Welcome to our video lecture on the nuclear atom. Our essential understanding for this lecture is that the mass of an atom is concentrated in its minute, very, very small and positively charged nucleus. So objectives for this video lecture, we're going to review the development of atomic theory from Democritus all the way, actually we're only going to go to Chadwick. We're not going to talk about Bohr or Schrödinger quite yet. We're going to review isotopic notation. So if I'm looking at something like carbon 12 versus carbon 14, what does that even mean? We're also going to review calculating relative atomic mass. Sometimes we call it average atomic mass. IB prefers to use the word relative. So those are our goals for this lecture. Before we get going too much, just take a moment to pause and ponder the magnitude of what we're talking about today. So Richard Feynman, who was an amazing physicist, famous and big thinking, wrote that if all of scientific knowledge, like everything, astronomy and biology and chemistry, if everything were to be destroyed and only one sentence passed on to the next generation, I believe it is that all things are made of atoms. So what we're talking about today, what we're talking about in class right now, like this big brain guy was like, this is the most important thing that we've ever figured out in science. All things are made up of atoms. So here's a quick look at some of the vocabulary that we're going to look at in this lecture. If you want to pause the video and look up any of these things before we get going, definitely do it. Otherwise, get ready, get set. Here we go. So again, our essential understanding, what IB wants us to come away with at the end of this lecture, is that the mass of an atom is concentrated. The great majority of the mass of an atom is in its minute positively charged nucleus. Little bits of background into how we have come to our understanding of what an atom structure is. So a really, really long time ago, these ancient Greek guys, Democritus and Leucippus, coined the term atomos, which means indivisible, because the thought was that atoms could not be divided. If you took a piece of matter and you chopped it into pieces and more pieces and smaller pieces, at some point you would get to a small piece of matter that could no longer be divided. Atomos, indivisible, the smallest piece of matter, can no longer be divided. So Democritus, Leucippus, ancient Greek guys, big thinkers, came up with this idea, which was really cool. And then like the what's it called? Middle Ages happened and not a lot of science was going on those days. We actually lost a lot of knowledge, but then the Renaissance and science made a return. And in the 1800s, John Dalton came up with this idea of atomic theory. And his atomic theory included lots of pieces of information, some of which are accurate and some of which we have edited just a little bit. So first he said that all matter is composed of atoms. That is accurate. All matter is composed of atoms. An element consists of atoms of only one type. This is no longer accurate because we know that isotopes and ions exist. So we can have different kinds of atoms in the same element. Dalton also said that compounds are atoms of more than one element combined in whole number ratios. For example, if we have H2O, 2 is a whole number, and here's an invisible 1, it's a whole number. And so a compound, we have some hydrogen, we have some oxygen, atoms of different elements that are combined in whole number ratios, 2 to 1. That's the law of definite proportions. Water is always definitely 2 to 1. We can also have multiple proportions, because I could have H2O, but I could also have H2O2, and this is a different proportion and therefore a different compound according to Dalton and his atomic theory. Finally, we're going to throw in the idea of Lavoisier, who was a tax collector in France in the 1700s. Not a good time to be a tax collector in France, but before he lost his head, quite literally, he came up with this idea of the law of conservation of matter, in which we're thinking that in chemical reactions, atoms are neither created nor destroyed, but they just rearrange in those compounds, in those molecules. Another cool thing about John Dalton, he was colorblind, and he was the first scientist to really document and think about being colorblind. And so since John Dalton was colorblind, it's always good when we're talking about John Dalton to make sure that we are not colorblind. So do a quick vision test and make sure that you can see the colors in the numbers in the bubbles. And if not, make an appointment with your doctor. All right, So enough about John Dalton. Let's talk about moving forward almost 100 years now and J.J. Thompson. So J.J. Thompson was a physicist, and he was doing some investigations into matter, and he took some matter and he put it in a tube and he zapped it with some high voltage electricity, so lots and lots of energy, which caused the matter to basically go into plasma states. We know that we've got solid, liquid, gas, plasma. Atoms have so much energy that their electrons fly off of them like lightning or plasma balls. So he basically invented the very first plasma ball, and he noticed that if you put a magnet around this stream of matter, that it would bend toward the positive plate and away from the negative plate. And so he knew that the sky was negatively charged because opposites attract, and if it's bending toward positive, it must be negative. So he discovered electrons. And so Dalton's idea of an atom was that they were just like solid chunks of stuff. So scientists have been working on that idea. J.J. Thompson was like, well, that's clearly not accurate because I've got these tiny little pieces called electrons. Well, he called them electrons. These tiny little pieces. So there's got to be at least something going on that's not just a solid chunk of matter. So he came up with this idea of the plum pudding model because he was British, and in Britain apparently they eat plum pudding, and the electrons, he surmised, were like little raisins floating around in a pudding, and that pudding was like gel-ish stuff that had a positive charge. So you would have these negatively charged electrons floating around in a pudding of positively charged stuff. And this is what an atom was. And for this, he won the 1906 Nobel Prize in Physics. Along comes his student, Ernest Rutherford, who decided to take some gold and mash it up super, super, super thin. Like, he hammered this until the gold was very, very thin, maybe just a few atoms thick. And then he took some radioactive stuff, alpha particles. Alpha particles are basically helium nuclei, so 2 protons, 2 plus 2 neutrons makes a mass of 4. No electrons. So these alpha particles are the nuclei of helium atoms, and he could shoot them at the gold. And what he assumed would happen if the gold was in fact big gels of positively charged matter with electrons floating around inside, that these positively charged things would bounce off the positive and go right back. He expected those positively charged things to just bounce and come right back. But instead, he detected with his detecting screen that the great majority of these alpha particles actually went straight through the gold. They went straight through the gold and hit the other side. Some of them did bounce back a little bit. Some of them got deflected a little bit, but the great majority went through the gold. And so he came up with this idea that instead of having this blob of positively charged stuff, plum pudding, if you will, that maybe atoms were more of a solar system kind of shape, where we have that positive charge, that nucleus, very small at the center of the atom, and that those electrons are orbiting around that positively charged nucleus. So Rutherford discovered the nucleus, positively charged, very, very small. The great majority of the mass is in that very small nucleus. For this, he won the Nobel Prize in 1908. H.G. Moseley might be one of the most tragic stories in all of science. So Moseley was in his mid-20s when he was doing chemistry and physics investigations, and he figured out that the atomic number is equal to the number of protons. Prior to Moseley, the periodic table was arranged with elements in increasing mass. So hydrogen was number 1 because it was the lightest, and helium was 2 because it was second lightest, and lithium was 3rd because it was the 3rd lightest, and we just went on getting heavier and heavier from there. It was Moseley who determined that hydrogen is number 1 not because it's lightest, because it has 1 proton, and helium has 2 protons, and lithium has 3 protons, and etc. This is fundamental to our understanding and our identification of atoms. And it was this guy in his 20s who figured it out. So Moseley's law, atomic number is equal to the number of protons in the nucleus of an atom. When Moseley was in his 20s, he was sent off to World War I. And at the age of 27, he was killed. And Isaac Asimov, another really amazing physicist, said that, considering what he could have accomplished, because he already did in his 20s, what he could have accomplished if he had survived past the age of 27, this might be the single most costly death to mankind ever. So really tragic story, what Moseley accomplished in his very few years of doing science, what he could have accomplished if we didn't have war. Good. Okay, so, no, not good. Sad. Loss. Moving on. So we found the electron. J.J. Thompson did that. We figured out that the nucleus exists. That was Ernest Rutherford. Interestingly, Rutherford was a student of Thompson. And then this guy, James Chadwick, he was a student of Ernest Rutherford. And Chadwick discovered the neutron. So again, we took some alpha particles and we shot them at first beryllium, and then some things happened and things flew off the beryllium, and then he shot the stuff from the beryllium at paraffin wax. It was kind of a weird thing, like all these different layers of stuff getting shot at other stuff. And then he finished up with detecting it with a Geiger counter and realized that there had to have been some pieces that had no charge flying out of nuclei. And so he discovered the neutron. And for this, he won the Nobel Prize in 1935. So Thomson, electron, Rutherford, nucleus, Chadwick, neutron. All right, so quick review of these subatomic particles. Remember, again, the proton was discovered kind of sort of by Rutherford. It was really more the nucleus that Rutherford discovered. Protons are found in the nucleus. They have a charge of +1. They have a mass of about, not exactly, but about 1 AMU. AMU stands for atomic mass unit. Neutrons also in the nucleus. They have 0 charge. They're neutral. Also have a mass of about 1 AMUs. These guys do not have the exact same masses, just almost the same. Electrons have a charge of -1, and I'm gonna say that it has a charge of about 0. There is, not charge, mass, a mass of about 0. Electrons do have mass. They are made of matter, but the mass is so small that we round down to 0. But they do have mass, just not very much. And those electrons are found in electron clouds. So if we're thinking about how big even is an AMU, AMU, 1 atomic mass unit, is equal to 1.66 times 10 to the negative 27 kilograms. And you don't have to memorize any of this because it is in sections 2 and 4 of your IB chemistry data booklet. So let's talk about isotopes. So remember that isotopes are atoms of the same element that have different numbers of neutrons and therefore different masses. Always the same number of protons, always, but different numbers of neutrons and therefore different mass numbers. Here we have examples of isotopes of hydrogen, protium, deuterium, and tritium. So protium has 1 proton, its mass is 1, and that's it. This guy, deuterium, has a proton, always only 1 proton because hydrogen only has 1 proton, but it also has a neutron, and so the total mass of this guy is 2. This guy, hydrogen, once again has only 1 proton, but now it's got 2 neutrons, total mass number of 3. Because these guys have different numbers of neutrons, 1, 2, and 0, they are isotopes of hydrogen. Different numbers of neutrons, different masses, but always the same number of protons. We can show isotopes with a couple different kinds of notation. So here's probably my favorite one just because it's so quick and easy. So we're going to put the element symbol as X. Z is the atomic number, which according to Moseley is the number of protons. And then A is going to be the mass number. Mass number is equal to the number of protons plus the number of neutrons. When we combine these two guys, protons and neutrons, we call these nucleons. These are all the things that are in the nucleus. protons and neutrons combined to make the nucleons. We can analyze our isotope notation to figure out how many things are in each of these particles. So this isotope of magnesium, this particle is going to have always 12 protons. Always 12 protons in magnesium. If it has a different number of protons, it's not magnesium. This is our mass number. It is equal to the protons plus the neutrons. 26 is equal to 12 protons plus some number of neutrons. If I subtract 12 from both sides, we get 14 neutrons, because 26 is equal to 12 plus 14. So there's no charge over here. Notice down here we've got a charge. Up here we don't have a charge, which means this atom of magnesium is neutral. Neutral atoms have equal numbers of protons and electrons. So this atom of magnesium has 12 protons and 12 electrons and 14 neutrons. This guy, magnesium, 24. So this is going to be our mass number. Again, 24 is going to be equal to the number of protons, which in magnesium is always 12, plus some number of neutrons. 24 minus 12 is going to give us 12 neutrons. 14 neutrons, 12 neutrons. Different numbers of neutrons, but the same number of protons means that these are isotopes of each other. These are different isotopes of magnesium. This guy, same mass number, 26 and 26. So this is also going to have 12. Notice that our 12 here is invisible, but it's magnesium. It always has 12 protons. 12 protons, 26 minus 12 is going to be 14 neutrons. But now I've got a charge. And this positive charge means that I have two more positive things than I have negative things. I have two more protons than I have electrons. 12 is 2 more than 10. 12 protons is 2 more than 10 electrons. So this particle of magnesium has 10 electrons, not 12 like this guy up here. This is a neutral atom. This guy is no longer neutral. It's got a charge, which makes it, we're going to throw in new vocabulary. Well, not new, more review vocabulary. It's an ion. So lots of isotopes are radioactive, and we use them to do super cool things. Cobalt-60 is used to treat cancer and radiotherapy. Carbon-14 we use in archaeology to date artifacts, like how old even is that pot. Iodine-131 we can use to diagnose and then treat thyroid cancer. Iodine-125 we use to treat brain and prostate cancer. All of these guys emit energy that we can put to work. We can also use that iodine-131 in SPECT imaging. Basically, we throw this radioactivity into a brain, and then how the iodine-131 emits its energy allows us to understand how the brain is working while this person is alive and thinking and doing things. So crazy, crazy cool. Another cool thing about radioisotopes, so they have half-lives. Half-life is how long it takes for half of the radioisotope to decrease in mass in numbers of atoms. And so carbon-14, which we use to date archaeological artifacts, has a half-life of 5,730 years. What that means is this: if I had 100 grams of carbon-14 to start, after 5,730 years, I'd only have 50 grams left. The other 50 grams would have turned into nitrogen-14. Another 5,730 years later, what would that be? 13,460, I think. We're going to go from 50 grams down to half of 50 is 25. So this is kind of quirky. We don't go from 100 to 50 to 0. It's not the other half, but it's half of what's left over. 100 to 50 to 25 grams are left. The other 75 grams are again nitrogen-14. Another 5,700 years, we're going to chop this in half. Now I only have 12.5 grams of carbon-14 left, and it just keeps going and going and going. Really, really cool. And we, as I said, we use carbon-14 to date archaeological artifacts, but sometimes technology changes and so does our data. And so in 1988, we dated the Shroud of Turin, which is a religious artifact, and scientists were like, oh, it's actually pretty old. And then in 2013, a different group were like, well, actually, if we look at the flax instead of the cotton, maybe it's a lot older. And so just know that Even our great techniques get better over time. And one of the most amazing things about science is that it's always getting better. We're always learning more. All right, so the last piece of the last objective for today's lecture is relative atomic mass. The definition of this is going to be the ratio of average mass of an atom to the unified atomic mass unit, or the AMU. So we're going to find the average mass of all the isotopes of an element. We're going to compare that to the AMUs. So if these guys are in AMU, and I'm making a ratio, which is like a fraction, also to the AMU, these guys cancel out, which means that in IB world, relative atomic mass has no units. It is unitless because the AMUs top and bottom cancel out. It's the ratio of the average to an AMU. We're going to look at the weighted average of all the different isotopes of that element. And what this means, weighted, is kind of like how we do grades, where summatives count for more than minors count for more than formatives. And so we're going to look at abundance, how much of each isotope exists, not just what its mass is. How do we know the masses and the abundances of different isotopes, of different elements? We use this amazing machine called a mass spectrometer. How even does a mass spectrometer work? Let me tell you. So what we're going to do first is we're going to throw our sample, perhaps it's magnesium or hydrogen, we're going to plop it into the machine. We're going to heat it up to vaporize it. So we're going to turn it into a gas because we want those particles to be separate from each other, able to pop around, move really easily, and gas particles move really easily. And then we're going to zap it with a bunch of electrons to ionize the sample. So we're going to make it positively charged. That's important because we're going to send it through a magnet, and we know that things that have charges get pulled and pushed around by magnets. We're going to then accelerate our particles, speed them up, smash them through our magnet. What happens is this. The positive particles are attracted to the negative side of the magnet. They are repelled by the positive side of the magnet. And so our positive particles are going to bend, but they don't bend the same. The lightest guys, the guys with the least amount of momentum, are going to bend the most. The guys that are heavier, they have more momentum. We cannot push them around quite as easily. They're going to bend a lot less. And so at our detector, at the end of our beam, we can see that things are hitting the detector in different places. Because they were lighter, they got pushed around a whole lot more by the magnet. The guys in the middle and the guys that were super heavy barely got knocked around by the magnet. So I can separate my different masses by how much the magnet can push them around, but also we can see how many times they hit in these spots, and that will give us our abundance. The data is going to look like this. So we threw some sample into our mass spec, and I've got 1, 2, 3, 4, 5 pieces of data. So we have 1, 2, 3, 4, 5 isotopes. I'm going to use a different color so you can see me annotating the graph. And what we can do is we can kind of go across to our abundance, and we can see that about half, about 50% of all of the particles that hit the detector had a mass of 90. So the abundance of the isotope that has a mass of 90 was 50%. This guy at 91, I don't know, maybe like a 13 or 14, and this guy at 92, maybe almost a 20. I'm not doing a very good job of drawing straight lines here, but you can envision that we can match up how many particles hit at each of the different masses because of that amazing mass spectrometer. And then we can take that data and we can do some math. What math do we do you ask? Well, super easy. We're going to first turn our abundances into decimals, and then we're going to multiply those decimals by the mass. Last step, we add. So first decimal, then multiply by the mass, and finally add. So to do that with this problem, I'm going to take my abundances that are in percents and turn them into decimals. We do that by dividing by 100, moving our decimal backwards 2 places. So this is going to be 0.199. And then this one, go backwards 2, divide by 100, 0.801. Next step, multiply by the mass. So we're going to take the mass here, 10, and multiply it by the decimal abundance. I can actually do this in my head. It's 1.99. take this guy, my 11, and multiply it by 0.801. I can't do that in my head. Hold on. Let me grab my calculator. Oh, geez. There it is. Sorry. 11 is the mass times the decimal abundance 0.801 is going to give us a mass of 8.811. Last step, add. So we're just going to add those up, and that's going to be, according to my handy dandy calculator, 10.801. Because we are making a ratio of these AMUs to the original AMU, our units cancel, and so our final answer is unitless. This is the relative or average atomic mass of these isotopes of boron. And this makes good sense because 10.8 is closer to 11 than it is to 10, which it should be because I have 80% boron 11 and not even 20% is boron 10. So 11 should count way more in our average than does 10. All right, let's do a couple more practice problems. I would love for you to pause the video, do these on your own, and then I'm going to go over the answers, but pause and work and then replay. All right, hopefully you found some answers. Let's do this guy first. So calcium with a charge of +2. This bottom number is our atomic number. It's always equal to the number of protons. So this guy has 20 protons. Calcium always has 20 protons. Neutrons, I'm going to do neutrons next. We're going to take our mass number. 39 is going to be equal to the number of protons plus the number of neutrons. We have 20 protons because it's calcium. 39 equals 20 plus, and subtract that 20 from both sides, and we are going to have 19 neutrons. To find the number of electrons, we have a +2 charge. That means I have 2 more positive things than I have negative things. If I have 20 protons, then I have 2 fewer electrons. That's going to be 18. 18 electrons, 19 neutrons, 20 protons in this particle of calcium. All right, this guy, remember that we're going to turn our percents into decimals, multiply those decimals by the masses, and then add. So this one's easy. 75% has a mass of 10 AMUs. 0.75 is the decimal version of that. Times 10 is the mass is going to give us 7.5. What about this one? The other isotope has a mass of 8. I don't have a percent. How am I going to do this math? Well, remember that percents add up to 100. So if this guy is 75%, what's left over? This guy has to be 25%. Turn 25% into a decimal. It is 0.25 times 8. 0.25 is about a quarter. A quarter of 8 is just about 2. We're going to add those up and we're going to get 9.5. 9.5 is our relative atomic mass. Not 10 plus 8 divided by 2 is 9, but 9.5, because a lot more is 10 than is 8. All right. If you have questions, bring them to class. Otherwise, let's do a check to make sure that we did all the things that we were supposed to do. Do we understand that the mass of an atom is concentrated in its minute, very, very, very small, positively charged nucleus? Yes. Rutherford's investigation was essential to that understanding. That is an essential understanding. The objectives. Did we review development of atomic theory? We did, mostly just focusing on the nucleus. So we talked about Democritus, we talked about Dalton and Thompson and Rutherford, and we stopped at Chadwick and the neutron. We'll talk about Bohr and Schrödinger when we talk about electrons. We reviewed isotopic notation. Remember that carbon-14 versus carbon-12. If it's got a charge, these are our ways to denote isotopes. And then how to determine and calculate relative atomic mass. How to determine, we use a mass spectrometer, which is a super cool machine. And then calculating relative atomic mass, we're going to turn our percents into decimals. And then we multiply by the mass. And then we add them all up, and that's our final answer. If you have questions, bring them to class.